How do you analyze a parallel RLC circuit efficiently? Imagine you're trying to understand how a circuit responds to different frequencies. You want to find out how it behaves when the inductor and capacitor work together. That's what analyzing a parallel RLC circuit is all about. Let's walk through the steps to do this smoothly and accurately. First, picture the circuit. The resistor, inductor, and capacitor are all connected across the same voltage source. This means the voltage across each element is identical, which makes analysis easier. Next, since we're dealing with alternating current, we use phasors to representing voltages and currents. Phasors are just complex numbers that make sinusoidal signals easier to work with. Usually, we choose the voltage as our reference with zero phase angle. Now, instead of impedance, we focus on admittance, which is the reciprocal of impedance. Admittance adds up in parallel, so it simplifies calculations. The admittance of the resistor is 1 over R, which is purely real. For the inductor, it is 1 divided by J times omega times L, giving us a negative imaginary number. The capacitor's admittance is J times omega times C, which is purely imaginary. Here, omega is the angular frequency, calculated as 2 times pi times the frequency. Once we have the individual admittances, we add them together to find the total admittance. This total is a complex number with a real part called conductance and an imaginary part called susceptance. The total current supplied by the source can then be found by multiplying this total admittance by the voltage phasor. When the circuit reaches resonance, the inductive and capacitive susceptances cancel each other out. This happens when omega times C equals 1 divided by omega times L, which leads us to the resonant frequency omega 0, equal to 1 divided by the square root of L times C. At this point, the circuit's admittance is purely real, and the impedance is at its maximum. To understand how the circuit impedes current, we take the reciprocal of the admittance, giving us the impedance. The magnitude and phase angle of this impedance tell us how much the circuit resists current flow and how the current and voltage relate in phase. The quality factor, often called Q, measures how sharp the resonance is. It is calculated as R times the square root of C over L. A higher Q indicates a narrower bandwidth and a more selective response at the resonant frequency. To visualize these relationships, phasor diagrams and impedance triangles are very helpful. They show how the currents and voltages relate and help you see the balance between resistive and reactive parts. For more complex circuits or verification, Kirchhoff's laws are useful. The current law states that the sum of currents at a node is 0, and the voltage law says the sum of voltages around a loop is 0. Using these laws in the phasor domain helps you solve systematically. In practical terms, these circuits are used in tuning and filtering, especially in radio frequency applications. Knowing how to analyze them allows you to design circuits that select or reject specific frequencies. Understanding resonance and impedance behavior also helps in power factor correction and signal processing. By following these steps, you can analyze a parallel RLC circuit efficiently, predict how it responds to different signals, and apply this knowledge to real-world electrical systems.